If you walked into a modern pharmaceutical lab right now, the air you're breathing is cleaner than a mountain peak. That creates a paradox because humans are contamination machines. A standard room acts like a dirty fish tank. The air is a closed system, so if you shed a skin cell or exhale a microbe, it stays there, suspended in the environment. In a facility manufacturing injectable drugs, a single lingering particle ruins an entire batch of medicine. To solve this, contaminants are never allowed to settle. If a threat is introduced, it is pulled upward and eliminated through the ceiling. Sterility isn't about filtering the air you already have. It's the active, continuous ejection of the environment itself. Engineers measure this cycle using a metric called ACPH, air changes per hour. We aren't circulating air. The entire room volume is being displaced. According to the FDA's Aseptic Guide, an ISO 8 cleanroom requires 20 air changes per hour. For high-grade sterile manufacturing, that rate hits 240 replacements per hour. At those speeds, the room functions as a high-velocity air engine. Calculating that velocity requires locking down two specific variables. First, calculate the physical volume. We multiply length, width, and height for the total cubic feet. Next, measure the incoming duct airflow in cubic feet per minute, or CFM. Finally, multiply CFM by 60 and divide by the room volume to get the ACPH. This calculation allows engineers to scale sterile environments, whether they are building a single closet or a massive manufacturing wing. The math only works if we can capture the CFM directly at the HEPA filter source. To do that, engineers deploy a specialized instrument called a digital thermal anemometer. Look at the physics. It operates on the king of cooling principle, using a microscopic heated wire probe. As air flows, it cools the wire. The instrument tracks the current required to maintain heat. Faster air causes more cooling, demanding more current for the speed reading. For larger air ducts, we use a mechanical alternative, the Vane Anemometer. It functions like a high-precision windmill. Moving air turns the blades, and a magnetic sensor counts the rotations to establish the airflow rate. Without these sensors capturing real-time data, the math of our cleanrooms would remain purely theoretical. This entire ecosystem of math and measurement exists to control one vital metric: recovery time. If a technician sneezes or a sterile bag tears, recovery time is the window required to return that space to zero contamination. In this comparison, a system running at 10 ACPH struggles to clear the air. On the right, at 60 ACPH, the suspended particles are flushed from the environment instantly. In pharmaceutical manufacturing, these metrics are the line of defense protecting patients from contaminated medication. I've pinned a sheet in the comments detailing the exact ISO classifications and their required ACPH rates. The invisible air in a cleanroom is a hyper-engineered survival tool, which is exactly why